All right, well, welcome everybody. We're going to go ahead and get started. We're all here for Sam's thesis defense. Sam came in to the department a couple of years ago and from NIU, and we kind of quickly started getting interested in using some of the structure for motion data sets. We had just recently gathered one of the storms that had tracked through the area. Sam kind of picked this up and ran with it, kind of made it his own. We've got a lot of stuff in here. So the presentation is called Detection of Tornado Damage via Convolutional Neural Networks and Unmanned Aerial System Photogrammetry. I see we've got a lot of people from the lab here. We've got the two committee members, Craig Ramsayer and Yang Xiao are both here. So many of us have probably done this before. For the people that haven't, we'll just kind of outline here how this is going to go. Sam will present his research for about half an hour or so. We'll have a public period of questions and answers where anybody that's here can ask Sam some questions about it. And then we'll move to a closed session where Sam and the committee will meet for a time and kind of dig into some of the details. And we'll go from there. So with no further ado, I will pass things over to Sam and we'll get to see the presentation. So thanks, Sam.
Yeah, thank you for the introduction. Welcome, everyone. I'm excited yeah, I appreciate everyone coming out here. This is fun. So I'll jump into my presentation. So let me start sharing my screen. Can everyone see a PowerPoint slide? Yeah, we're good. All right, cool. Let me just get this set up. Turn on my laser pointer. All right, cool. All right. Okay. We'll get started now. Hello, everyone. Welcome to my thesis defense. Today, I'll be presenting my thesis titled Detection of Tornado Damage via Convolutional Neural Networks and Unmanned Aerial System Photogrammetry. There we go. Okay. In this research, I developed a CNN that classifies tornado damage in forested areas using drone-derived orthophotos and digital surface models. This method can help fill a gap in tornado damage assessments, as tornadoes that occur in wooded areas are typically difficult to survey. The graphic to the left shows the intersection of UAS photogrammetry, tornado damage, and machine learning to form the area of automated detection of tornado damage. Problem: post-tornado response and recovery operations require a comprehensive impact assessment in order to protect lives, property, and accelerate community recovery. The National Weather Service still heavily relies on community reports and ground-based assessments to generate event reports. Ground-based collection methods is a resource-intensive process that often leads to uneven coverage, missing data, and slow report turnaround time. These issues are especially prevalent in areas of forest damage, where terrain and remoteness can restrict the surveyor's ability to assess damage. My hypothesis is that a convolutional neural network that incorporates terrain and image derivatives will perform better than an RGB-only convolutional neural network. In addition, a CNN-based method will classify tornado damage in undeveloped and forested areas more accurately than traditional remote sensing technique of random forest classification. Why UAS for damage detection? UAS offers users the ability to rapidly collect imagery, conduct variable change detection, and build three-dimensional models from the camera parallax. This can all be done with systems that are readily available to consumers. UAS has demonstrated capabilities in a variety of damage assessment environments. For example, building damage in earthquakes, forest fires, and property damage from hurricanes, tornadoes, and windstorms. Structure for motion derived digital surface models have added value to a variety of damage assessments. For example, flooding, coastal storm damage, earthquakes, wildfire, and winter storm damage. In the image on the right, Hangvarna et al. Calculated the difference between pre and post DSM to measure forest damage from a winter storm. Convolutional neural networks have recently been used in a variety of remote sensing classification applications, including damage assessments. CNNs are a type of deep learning algorithm that is designed to mimic the way an animal's visual cortex neurons interpret images called visual field. The input image is passed to a convolution layer, which applies a kernel function to each channel of the imagery. The results of each channel kernel output are summed into a single channel output called a convoluted feature. The first convolution layer reduces input image dimensionality, but several convolution layers can be used to increase feature extraction. The output is then passed to a pooling layer, which focuses on extracting significant features to reduce the dimensionality. The pooling layer applies either a max pooling maximum pixel kernel or an average pooling mean pixel kernel. Max pooling allows for greater noise suppression, which can improve overall performance. The output is then passed to a fully connected layer, which attempts to find nonlinear combinations in the output. The output is then converted into vectors that are passed to a feed-forward neural network, also known as a multi-layer perceptron. After several iterations or epochs, the feed-forward neural network identifies features that can be classified with a softmax technique, a type of supervised classification. After this phase is complete, the output is a model that can be used to classify data. How have convolutional neural networks been implemented in remote sensing-based damage assessments? Hidari and Montrakis 2019 reviewed different deep learning approaches to remote sensing monotemporal classifications. Monotemporal classification is a type of classification where only the post-event data exists. For example, on the right, there's two aerial images of pre and post-event damage from Hurricane Michael 2018. Multitemporal analysis looks at both of these images to detect differences. Monotemporal methods only have the post-event imagery to conduct analysis. Hidari and Montrakis 2019 found that CNNs were the most used monotemporal classification technique, and that CNNs generally perform better than other deep learning methods. Recently, Esri ArcGIS Pro released a deep learning module to facilitate remote sensing classification. The module can break rasters into tiles, commonly referred to as chips. Classify those chips with true data and train a model. Then that model can classify imagery that it's given. It can facilitate several different workflows, including pixel-based classification, which I am conducting in this study. How has UAS and computer vision been used to detect tornado damage? Official tornado damage assessments are conducted by the National Weather Service, usually via ground-based assessments. Forest damage is often underassessed due to resource limitations and physical barriers. Several studies, for example, Wagner et al. 2019, have deployed UAS to investigate tornado damage. The authors have found that UAS is a beneficial tool to collect damage imagery. The use of machine learning and computer vision to detect tornado damage from US photogrammetry is extremely limited. Canada et al. 2016 created a supervised maximum likelihood classification algorithm in ArcMap to classify forest damage and found a significant relationship between the classification severity with the ground truth assessment. Wagner et al. 2019 found that UAS outfitted with multispectral cameras add significant value by improving tornado path detection over simple RGB imagery. Wagner et al. 2020 presented ongoing research on the use of UAS structural motion orthophotos and a segmentation-based deep neural network, or DNN, to detect damage to roofs and residential homes. Their method identifies a residential roof and then classifies each roof into a different damage classification. For example, a binary damage, no damage, or a multi-class degree of damage, like severely damaged, moderately, no damage. Chen et al. 2021 quantitatively assessed several deep learning model schemas and model backbones for tornado damage detection. They found that binary classification, damage, no damage, had a higher total accuracy rate than multi-classification systems, for example, major, minor, and no damage. In addition, a DenseNet 161 backbone with a binary schema had the highest total accuracy at 84.8%, along with multi-class schemas. A ResNet Res Next 101 performed the best at a total accuracy rate of 81.5. Excuse me. Data sources. The data for this study comes from the April 19th, 2019 Franklin County, Virginia tornado. According to the National Weather Service, the tornado formed at 10:25 a.m. just north of Oak Level and traveled for approximately 13.2 kilometers, where it dissipated just east of Henry Fork at around 10:35 a.m. The tornado reached a peak intensity of EF3, Enhanced Vegeta Scale Level 3, which is a maximum wind speed of 159 miles per hour, which is an estimated maximum width of 250 meters near Windy Ridge Road. According to the National Weather Service surveys, 2019, the tornado severely damaged 3 structures, destroyed 10 outbuildings, and caused 2 injuries and no deaths. The path of the tornado is highlighted in black. Daniel Cross of Virginia Tech Department of Forest Resources and Environmental Conservation collected a 3.6 kilometer section of the tornado on April 29th with an EV fixed wing UAS. Cross collection in my study area is highlighted in red. Then on the right of the map is a structure for motion orthophoto reconstruction of the study area. Of the study area on the right. Structure for motion results. The images collected by Cross were then processed with Pix4D, a commercial structure for motion product. The program takes the images collected by the UAS and with the image metadata like GPS location and camera specifications. The software will try and find common tie points or features. These tie points can then be assembled together to form a 3-dimensional point cloud. The point cloud can then be used to create an orthorectified photo and digital surface model. On the right is an animation of the Pix4D point cloud output visualized in Cloud Compare. Pix4D was able to match 557 photos of the 601 collected. The resulting ground sampling distance was approximately 2.8 centimeters. In order to reduce complexity and computation time, we upscaled the imagery to 10 centimeters. After the point cloud was generated, I used Cloud Compare to remove erroneous points in ArcGIS Pro to generate the DSM. The resultant DSM did contain some holes, so I used ArcGIS Pro void fill function to fill the small gaps up to 4 pixels. Pictured here from left to right is the structure for motion orthophoto, the resultant DSM with the void fill applied and scaled to an unsigned 8-bit image, the multi-directional hill shade from the DSM, and the truth data damage polygons on the far right. When the DSM was upsampled to 10 centimeters, each derivative and raster layer was matched to the same resolution and pixel position. For the truth data, I manually classified the tornado damage with oval polygons indicating damage. Areas that were not identified as damage were tagged as no damage. On the right is a stick diagram of forest damage. This method was inspired by Mike Sporer of National Weather Service. It was a promising method, however, it was hard to accurately classify the damage and generate a classification schema. The polygon approach, as seen on the left, was a simpler schema that allowed for better coverage and classification accuracy. To generate the model input, the output orthophoto and DSM are pre-processed with Python scripts and GIS software to generate each derivative. To create the imagery derivatives, scikit image is used to generate entropy and LOG, or Laplacian of the Gaussian, from the single band grayscale of the RGB imagery. The DSM is processed with ArcGIS Pro and Saga GIS to generate CHM for canopy height model, hillshade, openness, profile and tangential curvature, standard deviation of slope, and vector ruggedness measure, or VRM. All the derivatives in RGB imagery are scaled with a 595% stretch and then converted to an 8-bit unsigned integer. This was done in order to satisfy the input requirements from ArcGIS Pro and to normalize each derivative. Lastly, each layer was then stacked together into a 14-layer multi-band raster. There we go. Here's a breakdown of each derivative layer rendered with a 595 split and converted to an unsigned 8-bit. Entropy is a measure of average level of order/disorder in a neighborhood within a grayscale image and is calculated using scikit image. Laplacian of a Gaussian is a second-order spatial derivative filter to highlight edges. The image is first convoluted by a Gaussian filter or a low-pass filter, and then passed to a Laplacian filter equivalent to general curvature and is calculated with scikit image. Canopy height model, or CHM, is the difference between the digital terrain model, or the ground surface, and a DSM, which may include vegetation, buildings, and other features. The resulting raster is a flattened surface model and represents surface features with the major elevation changes removed. This is calculated in ArcGIS Pro using secondary LiDAR-derived DTM. For this product, the Virginia Vigen LiDAR dataset is used. Multi-directional hill shade is an illumination of the DSM modeled from multiple angles, creating a 3D visualization of the surface. This is calculated in ArcGIS Pro. Openness is a neighborhood calculation of the sky visibility, including negative relief from a central pixel. This is calculated in Saga GIS. Profile curvature is a second derivative of the surface in the vertical plane. Profile curvature helps illustrate the rate of change of surface features parallel to slope. Negative values represent convex slopes, while positive values represent concave slopes. This is calculated using a neighborhood surface parameters tool in ArcGIS Pro. Tangential curvature is a second derivative of the surface perpendicular to the slope gradient. Tangential curvature measures the rate of change perpendicular to the slope. Negative values indicate convex slope and perpendicular plane in the perpendicular plane, and positive values indicate concavity. It is similar to contour curvature, which describes where the landforms bend out or in. This is calculated using neighborhood surface parameters tool in ArcGIS Pro. Standard deviation of slope is a variation of slope values in a given neighborhood of a central pixel. Low values indicate a more uniform surface. Positive values indicate a large variation in slope values. This is calculated in ArcGIS Pro with the focal statistics tool. Then lastly, vector roughness measure, or VRM, is a neighborhood metric of surface roughness based on vector decomposition of the surface in a specified neighborhood, calculated in Saga GIS. Model development. After the derivatives are generated, they are then stacked together into a multi-band raster. The raster and truth data are passed into ArcGIS Pro deep learning workflow. In ArcGIS, the imagery and truth data are chipped or broken up into small images, subsets of the training data for training. Specifically, we used 512 by 512 pixel chips with a 256 pixel overlap. So the input imagery is given, they're broken down into these little tiles, a 512 by 512 with 256 overlap, and that's what's used to train the model. In order to increase the training data diversity, each chip is rotated 90 degrees 3 times. So there's a set of images at 0 degrees, 90, 180, 270. Those chips are then brought together into the train model function. For this study, a UNet pixel classifier with a ResNet34 backbone is created. The output of the training function is a model that can classify pixels of imagery into damage and no damage. Here's an example of the training and testing data that I used. To effectively evaluate the model's performance, the multi-band raster is split into a training data set and a testing data set. The model is trained on the training data set and then tested on the testing data set that is used for classification. Again, the training data set is rotated 3 times, so 0, 90, 180, 270. The classification performance metrics were calculated from the testing raster with the truth data set. So after the model is built, the testing on the right is used. The model classifies what it finds as damage, and then we use that and my truth data that I generated for the whole study area to calculate the performance metrics. Several layers required a kernel size or neighborhood parameter for their computation. 3 circular kernel radii were tested to determine the effect of kernel size on the model performance. I chose 5 pixels, 25 pixels, and 50 pixels, or half a meter, 2.5 meters, and 5 meters respectively. These sizes were chosen to sample several plausible scales at which tornado damage would be apparent. For each of the 3 kernel radii, a model was created and assessed. Each model was run with a learning rate of 1 times 10 to the negative 5th at 20 epochs in order to compare the classification results of each model. These hyperparameters were chosen because preliminary testing indicated that these parameters would be close to the values, to the tuned hyperparameter values. The hyperparameter values were optimized in the full model that was created later. In this table, kappa scores are reported for each model type with different kernel sizes. Cohen's kappa, is essentially the accuracy of a categorical classifier with a chance of it guessing correct removed. Differences in kappa rates of the sizes were small, with 25 pixels showing the largest kappa accuracy score at 71.3%, followed by 50 pixels at 70%, and 5 pixels at 68.9%. Okay. Model output. Once 25 pixels was chosen, I took an iterative approach to optimizing the model performance. The optimal learning rate was found to be at 2 times 10 to the negative 5th at 25 epochs on the full data set. With these hyperparameters, the full model achieved a kappa score of 78% and an F1 score of 87.3%. To compare the results from the full model, an RGB-only model is created with the same hyperparameters. The RGB-only model achieved a kappa score of 73.5 and an F1 score of 85.8. In this figure, the original image is on the left, the multiband raster is center, and the RGB-only model is on the right, pardon me. Visually, the outputs of the 2 models are very similar. Both models classify a majority of the damage and avoid the grassy patch. On the right side of the images, it looks like the full model and RGB-only model have variations in classification of the damage. This table breaks down kappa scores and F1 scores for the full model, RGB, and random forest model. A random forest model was built in scikit-learn to compare a more traditional machine learning technique with the CNN output. The full model achieved a kappa of 78.0%, the RGB is 73.5%, and the random forest model with a kappa of 60.1. The full model is only 4.5% kappa more accurate at classifying damage than the RGB-only model. In addition, the CNN methods classified damage at a higher accuracy rate than the random forest model. On the right column, the F1 score is reported for each model. F1 score is the harmonic mean of the precision and recall of a classifier. The full model achieved an F1 score of 87.2%, the RGB 85.8%, and the random forest at 76.9%. Like the kappa scores, the full model achieved a marginally higher score than the RGB version and a larger difference between the random forest model. In order to understand the ability of each image and DSM derivative combined, each image and DSM derivative contribution to the overall convolutional neural network, separate models were generated for each band with the same hyperparameters as the full model. So this was done using a learning rate of 2 times 10 to the negative 5th at 25 epochs. So each derivative is broken apart, and then a single model or models built for each derivative by itself. These hyperparameters were not individually tuned for each model and may be contributing to under and overtrained models. However, the breakdown of each layer indicates that there are significant differences in the ability of certain layers to classify damage than others. The lowest performing derivatives were the image-based entropy and LOG, Laplacian of Gaussian bands. In contrast, the derivatives were much better at the DSM derivatives were much better at classifying damage on their own. Among the DSM derivatives, vector ruggedness measure, or VRM, performed the highest at 68.4% kappa, tangential curvature, openness, hillshade, CHM, or canopy height model, and the DSM performed around the same level of kappa from 58.5% to 63.5%. The lower performing DSM derivatives were standard deviation of slope and profile curvature at 49.2% and 38.1% kappa, respectively. The different kernel radii size, 5, 25, and 50 pixels, did not have a significant effect on performance. This could be an effect of the marginal increase over the RGB only model, so the 4.5 increase that the DSM or the full model had over the RGB only model. Additionally, each derivative might need to be individually tuned for the radius size. So the radius for each derivative might have been mismatched or might need to be tuned to a specific value that's not what we chose of 2.5 meters or 25 pixels. The RGB only model is quite predictive with a kappa score of 73.5% in comparison to the full model at 78% kappa. Comparing the CNN results to the random forest model, both the CNN models performed better than the traditional random forest model. The DSM derivatives appeared to be more predictive than other layers, especially VRM. This result is surprising considering Kuhner et al. 2016 found that both entropy and LOG to be useful layers in damage classification. The reason for these results is unclear. During the radii test, all radius-derived bands were set to the same value in order to reduce complexity of the experiment. It is possible that the 25 pixel radius was a better fit for the DSM derivatives than the image derivatives. Additionally, there is a reasonable chance that the DSM derivatives are a more significant addition to the model than the image derivatives. A more in-depth analysis of individual bands are needed in order to determine the exact relationship. In Wagner et al. 2020 and Chen et al. 2021, they showed that CNNs and deep learning algorithms can be trained to classify UAS-derived residential damage from tornadoes. They reported a total accuracy rate of 81 to 86%. In my CNN models, the total accuracy rate was 89.3% for the full model and 86.6% for the RGB only model. This result indicates better or comparable performance to Wagner and Chen et al. In addition, these models are a CNN pixel classifier. Their models in Wagner and Chen et al. Incorporate an object extraction layer and then classify the damage into different categories. The Chen et al. 2021 UAS tornado damage model, when trained with different model backbones, achieved a total accuracy of 84.8% with a DenseNet 161 backbone and a binary classification schema. Then they achieved a total accuracy of 81.5% with a ResNext 101 backbone and a multi-class schema. The results indicate that modifying the neural network backbones can have an effect on overall classification accuracy. In this study, only a ResNet 34 UNet pixel classifier was used. An interesting area of further research would be to compare the different pixel classifier backbones. In Menderes et al. 2015, they found that normalized DSM in the earthquake change detection classification method was able to achieve an overall accuracy of 96.5% and 90.7%, with a kappa score of 82.5% and 56.93%, respectively. The results in this research indicate that DSM products can add value to damage classification algorithms over orthophoto-only classification. Lastly, the Fujita et al. 2017 convolutional CNN tsunami damage model achieved an overall accuracy score of 94 to 96%, pardon me, which indicates that CNN can achieve a high degree of accuracy when detecting damage. Limitations. Throughout this research, several limitations were identified. To create the truth data, I manually classified damage with polygons from the RGB bands only. This RGB classification might have propagated to the model. There's a chance that this resulted in a model bias and might explain why the RGB classifies near the same performance as the full model. Another area of limitation was the kernel size evaluation. This research only chose one kernel size for the models. An individually tuned kernel size might have been needed for each derivative layer in order to extract more value. When the layers were stretched and stacked together, the 595% stretch might have had a negative impact on the overall model performance. Additional research is needed to evaluate the effect of this stretch and test alternatives. Areas of further research. Conduct an analysis of models and the sensitivity to different tornado damage types, environments, and damage scales. 2, retrain the models with more data and test the effect on the new model. 3, conduct an analysis inspired by Chen et al. 2021 to test different model backbones and the resulting classification performance. Lastly, experimenting with different optimization strategies for the derivative layers. To conclude, post-disaster damage assessments are a critical component to response and recovery operations. UAS platforms prove to be useful tools for imagery collection and for post-event surveys. A CNN model was built to identify tornado damage from UAS orthophoto, image derivatives, and DSM derivatives. Our results indicate that a deep learning approach performed better than other machine learning techniques, for example, random forest approaches. That the RGB orthophoto alone performed nearly as well as the full 11-layer model. That among the spatial DSM derivatives, the vector ruggedness measure and multi-directional hill shape performed the best. Here's my bibliography. And then acknowledgements. I'd like to thank my family, Maggie, my parents, Annie, Rose, and our dogs. Thank you for your love and support. I'm extremely grateful for Daniel Cross, for the data that Daniel Cross was able to provide. This whole project was possible because of your work and generosity. Thank you. And to Mike Sporer and Dr. Wagner for providing advice, facilitating this area of research, and helping bring together this cohort. Special thanks to the Department of Geography staff, my fellow graduate students, and the Near Earth Imaging Lab. Lastly, I would like to thank my committee, Dr. Ramsay and Dr. Shaw, for their guidance and insight. And I would like to extend my deepest gratitude to my advisor, Dr. Pingle, for the countless hours of mentorship, feedback, and patience. And that's all I got. Any questions?
Great. All right. Thank you, Sam. Yeah, let's move on to the questions. Put this in gallery form so I can see everybody. I think it's a small enough crowd that we can kind of make this free form. So if you've got a question, feel free to pipe in. If you don't feel comfortable doing that, feel free to type it in the chat, but we'll just let it go. I'll start out with one just to get the ball rolling. Sam, what were your favorite parts of this research over the last couple of years?
I think the iterative design a little bit. It can be a little bit slow, but it was awesome to see taking these kind of ones and zeros, right? This pixel-based data, feeding it to this model, and then giving it something it hasn't seen, and then having it classify. And when I was going through making my presentation, I was looking at my old models, and I saw like I had one model that was highlighting all the roads. I'm like, okay, how it's doing that? And then, you know, as you iteratively design and also adding like that rotation around each axis really helped with training the model and kind of reducing some of the weird quirks it was happening. That was really cool to see. Yeah.
Great.
I have one. So has the ArcGIS deep learning package and all that stuff, has that gotten any easier to use since we started using it like a year and a half ago?
So I haven't checked recently, like with the if they like what their release logs were, but it's basically the same. So what's nice about it is it's a turnkey solution for those who haven't used it. So you give it your data, you have a chip, it's really quick. you point it to the training data set, it builds a model, you set your hyperparameters, you choose what backbone, and it spits out a nice PyTorch model. But for this research, one of the problems we had, as Jack was alluding to, is we could only get to classify RGB only images. It wouldn't like anything with more than one band. So I had to dig down into the Esri API documentation, so the backend, and I found that you were able to give it multi-bands and then exclude bands. So like on RGB imagery, band 4 is alpha values. So I was able to tell the model, don't use alpha values, use only these. And then it would spit out a model with only those trained. So I guess to answer the question, it's about the same. It's a little difficult. If you want something custom, it takes a while.
Gotcha.
Hey, Sam, how do you see, like, ideally, how does a model like this become operational? What do you see its, maybe it's in value to like the National Weather Service? Where does it really provide some new value instead of, human-based surveys?
Yeah, so I see it implementing kind of two senses. One being kind of rapid collection. So the tornado passes over, the winds die down a little bit. You can send up a drone and get it back, pull out the little SD card, load the data into like a computer, and start classifying, building that structure for motion model and classifying. It's a little, depending on your hardware, it could be kind of resource intensive. Or alternatively, you could take this and bring it back to like the National Weather Service office. So the computer we were using had some pretty serious horsepower. So it was an i9, 128 gigs of RAM, and 8 gig graphics card. So if like an office has the resources to obtain that type of hardware, the second meteorologist comes back, you can throw in that SIM card, build the model, and then hit and run with a PyTorch, and it classifies it for you. Yeah, and right now the way that this workflow, it's a little knob turning, right? I have to kind of get the model to work or iteratively designed, and then defining variables and all that stuff. And it's a little manual. Ideally, future, it would be kind of like just a program that you hit run. Here's my images, use the Pix4D or whatever structure for motion software backend. Give me that ortho photo. Here's the DSM derivatives, and then here's the output pixel classifier. And then they can give like a shapefile to, or a spatial file to the end user or the public.
Cool. Yeah. Do you see this as like a long-term replacement for human surveys, or do you see it as something different than that?
So right now, this kind of research is focusing on forest damage. Ideally, especially with the work being done by Wagner et al., this would expand to more damage types like residential, and that you could just fly a drone or get an aerial survey like a little Cessna and take some images and just reconstruct the survey. Currently, I think it wouldn't be a replacement. It'd be a nice addition, especially if there's a tornado in a huge underpopulated area where, the big thing with these National Weather Service reports is people have to see it to call in damage, right? So if it's on their property, they're calling right away saying, oh, the tree fell down. And then they get those reports. In these rural areas or in these underpopulated areas where it's just forest, this model can sit there and classify. So being able to kind of decipher people's reports, so that kind of human perception of damage, and then also taking this model requires a lot of human in the loop kind of work. So as the state right now, I think primarily it would be human-based, going out there and kind of getting the reports, flying the drone, and then kind of filtering it through and getting a better picture of what the damage looks like.
Great. All right. Well, if there aren't any more questions from the public, then we'll just kind of get one last call here. Then we will close the public session, the public part of this. And again, thank you, Sam.
Thank you.